So for this example, we're given the following word problem. Let me go ahead and read what we have, and then I'll go from there. So we are asked to paint a 20 feet wall under a mural, or a 20-foot wall under a mural, as pictured below. So they give us a graph. I'm going to go ahead and do my best attempt to give this by hand. And the function is called m of x that models this. And they tell us the bottom border of the mural is modeled by this function. And they tell us that m of x is equal to 0.01 x minus 9 quantity cubed minus x plus 30. And they ask us, what is the area under the mural? Okay, so first of all, what is implied here is that we're going from 0 to 20 feet here. And then that's all we need to do this by hand. So if we're going to do this by hand, the key thing to realize is that the area underneath the border of this mural, right down here, well, that's an integral, right? By definition, the area under a curve is equal to the integral of that curve between those x values you're talking about, which would be 0 to 20 in this case. So if I set up the integral for this, it's going to be the integral as x goes from 0 to 20 of m of x dx. And what is m of x? Well, m of x is this function right here, 0.01 x minus 9 quantity cubed minus x plus 30. So if I go ahead and calculate this integral, I'm going to get 0.01 times x minus 9 over 4 to the fourth. So just double checking, if you were to take the derivative of this, you'd bring down the 4, they'd cancel out, the power would become a 3, and you would do the derivative of the inside, but the derivative of the inside of this would just be 1. So it doesn't cause any issues when you're integrating. It doesn't overcomplicate things. And now this x would be minus x squared over 2. And the 30 would just become plus 30x. And we're evaluating this from 0 to 20. Remember, when you have a definite integral, you don't need to include that plus c, because if you did, it would just cancel out when you did your bounds of integration anyway. So this is going to be equal to, now since this is kind of a nasty function, I'm going to go ahead and set it up, and then I'll be using the calculator to help me do this. So this is going to be 0.01, 20 minus 9 to the fourth over 4, minus 20 squared over 2, plus 30 times 20. And we have to subtract from all of that this when I plug in 0. So 0.01, 0 minus 9 to the fourth over 4, minus 0 squared over 2, plus 30 times 0. Be careful about this. People will tend to assume that the entire second half of this is just 0 when it's not. These individual terms are 0, but notice that 0 minus 9, that's going to be a value. It doesn't just 0 out. Okay, at this point I'm going to throw this in the calculator. All right, so let's plug this in. This is going to be 0.01 times 20 minus 9. Now, of course, you could do that first, whatever 20 minus 9 is, which would be 11. But I'm just throwing this in as is. Raised to the fourth. That's all divided by 4. Make sure when you're typing this in that when you do the exponent, your cursor is going to be hovering up there, so make sure to hop over. So it's divided by 4, and then minus 20 squared over 2 plus 30 times 20. Because that's so long, I'm going to go ahead and get this as one number right quick. So I hit enter. That gives me 436.6025. Minus, now this will be a lot simpler since these two terms are 0. So I'm going to do 0.01 parentheses negative 9, that's what 0 minus 9 would be, close parentheses, to the fourth power Again, remember to hop your cursor over, divided by 4. So that's giving me 16.4025. And then just do the subtraction. That minus that. And we get 420.2. So the area underneath this mural that we would paint with just, plain old paint below the mural is 420.2. Now, I did the integral and set all this up by hand and then used the calculator to do the gross part, just the arithmetic. But we actually could have done this entirely using the calculator. And there's even a note in the word problem that says, note, if using a graphing calculator, and then it gives us our window bounds. So I'm actually going to redo this just using the calculator, and it's going to be a lot easier. So let me go ahead and clear off the screen just because I like no clutter. Whoosh, calculator clear. Now, I'm going to go and put in this equation right here. So I hit y equals, and now I'm doing 0.01 parentheses x minus 9 boop, raised to the cubed. Make sure to hop your cursor down. Minus x plus 30. Okay. Cool. Now, before looking at the graph, I'm going to change my window bounds. So I hit window. Now it tells us to set our x-min to 0. So right now it's at -10. I'm just going to clear that and hit 0. Hop down to x-max. I'm going to change that to 20. Tells us to leave the x scale to 1, so I do. Y-min is going to be 0. So plug in 0. Y-max, they say, is 35. And the y scale should be 5. So I'll do that as well. Now I'll hit graph. Okay. So we see a much smoother, accurate version of this curve here. Now what I'm going to do, I'm going to do second calc. You see how number 7 actually is the integral symbol? So we're going to use that. So I'm going to just hit 7. Now notice it asks you for a lower limit and an upper limit, where our limits are 0 to 20. So I'm just going to hit 0 for x, enter, and 20 for y, or for x. X goes from 0 to 20. Hit enter. And notice it's shading all this in. It's going to go all the way to the end because our window bounds are matching that. Boop. And it tells us right there, the integral of f of x dx is equal to 420.2, which we got right there. And it even says right here that the bounds are from 0 to 20. So there we go. If we have a mural modeled by this function and we want to paint the area below it, then we're going to need 420.2, I'm going to assume gallons of paint, whatever your units of measurement are for the area under this curve. And that is this example.